Hey, today we're going to be doing a linear regression by ourselves by implementing the gradient descent on our loss function, which will be the mean squared error. Okay? I know it sounds like a lot, but we'll go over everything, okay? And yeah, take it small steps, okay? So this video is going to explain everything from what is a linear regression to residual to all those fancy words, right? And I'm going to put nice little chapters in them so you can feel free to skip ahead if you know some area perfectly, right? So, let's start, shall we? Yeah. Okay. So, starting off, I feel like it's good to get our dataset, okay? So, we're going to be using a simple dataset. I got this thing from Kaggle, yes? Kaggle is that open source AI community from Google. So I have a GitHub repo, ML datasets with a bunch of CSVs, right? You should create one of them too, okay? So this is simply what it looks like. We have two columns, years of experience and salary. And we want to find a linear relationship between these two, right? You'll see it nicely when we plot this in a scatter plot, right? So basically that's what linear regression is. We're trying to find a linear relation between the salary, like is there any relation between the years of experience and the salary? And can we put a line through it and use interpolation and extrapolation to find values, okay? So that's in essence what the linear regression is all about. That's the main problem we're trying to tackle here, right? Likewise, you can have multiple columns and multiple dimensions, and it gets really messy there. Not too bad if we can get the grasp of it. I'm in the journey of that. But for now, let's focus on a simple 2-column one, right? So here's our CSV. If we look at the raw one, you can click raw, right? And bam, we have it. Quite a small one. Just 2 columns and 30 rows. Very simple, but we don't want to flood it with too much. This is our first try, yeah? Okay, and again, when you click raw, you get the raw URL, which you can directly import, right? So, yes. So let's go. So again, I'm going to be using Google Collab, right? It's essentially a Jupyter notebook, but cloud, right? It's fully free, and it's a blessing, honestly, right? It allows generally these kind of stuff. If you want to load data, I mean, not for the example, but generally, it's good to always use this, right? Opposed to your thing, because my laptop has 8 GB RAM. You can't do much with that with Google Open. And OBS too, memory hoggers. Okay, let's start. So, there's going to be some libraries we're using. Don't worry, we're not going to use the linear regression. We're not going to get a library. No, we're going to do that by ourselves, okay? So one thing we're going to use to handle our data is pandas, right? So we can import that fella. Import pandas as PD. It's an alias. People usually put that. NumPy is an NP, pandas is that, scikit-learn is SK, so on. So that's an alias, okay? And let's load our data. So here's our data. It's in this live URL. GitHub, and we can do df, which is an abbreviation for data frame, and there's a method from pandas called ps.read csv, right? Bam, we can load our thing in, and let's print our data sets. df it's taking quite. Bam, there it is, right? There's our nice dataset loaded into us, right? And here we have the index, we have years of experience and the salary, right? So number one, we can start. This is I think it's in I'm not sure what the data type is loaded as, but anyways, we can simply destruct. Let's take the salary only, bam, and let's take what's the other one? Years of experience. Years came, no? Cool. Years of experience, like that, right? That's how we can access our 2 values, right? So, good. Okay, now let's visualize the data, right? Let's dump it into a scatter plot. So for this, we're going to need matplotlib. It's basically a really awesome graphing. Not graphing, just it's a way of putting out your stuff. Okay, and oh yes, let's add some text. Keep it nice and neat, because over here, right, you can make this whole Jupyter Lab thing very aesthetic, right? You can add headings, simple markdown. Okay, load. How about let's call this big section what? Load data. Load the data. Yeah. Okay. Bam. Put it up. That's how you shift shells. Shift it up and down. And as you can see here, we have a section, and we can run the sections. It's very good, and let's run all here. That's very useful when you're just coming back from like a holiday or something. Okay, load data, and let's under here put visualize data. Okay, second heading, bam, there, cool. And let's add some code. So, matplotlib, import matplotlib dot pyplot. This is the one we're looking for, right? So let me just copy some code real quick. I did this bit, did my homework. Okay, let's go through this line by line. Figure, so basically we're creating a figure, 10, 6, those are the dimensions, and the x and y. What is the two values, right? So do you remember from here, right, we printed just the whole x column, big array of those, and a big array of salary, right? There, and the title, x label, y label, and showed grid, and we show it. So these are self-explanatory. And yeah, here's the main thing, right? We're just passing in those two stuff. And if we go for it, why is it slow? My Wi-Fi. So here we are. Here's our magnificent scatter plot, right? Bam, look at that. Okay, so as you can see, we have years of experience and salary, right? So each item, right? So if we explain this data set, right? So 1.2 years of experience, some guy has got 39k. Another guy with 1.4 years of experience, he got 46k. Another guy with 1.6 years experience, he got 37k, so on and so forth. So that's what the data represents, right? This guy got 40,000 with roughly what? 2.3? Roughly 2.3, right? This is 3 and 2.3, right? So this is how the data is represent. Each what do you call it, row is a person, right? So they went out and asked about 30 people, what happened to you? How many years of experience have you got, and how much are they giving you? Okay? So that's what the situation here is, okay? So now from here, we're going to want to get a line, right? So let's get a whiteboard here, because I'm going to do some explaining now. Let's add an image, scatter plot. This is the image of our scatter plot we just had, okay? So, what are we trying to do? Let's draw a line real quick, add a shape, a line, and like that, okay? So this is the big thing, right? We're trying to get a line to go through here. Okay, and from this, we're gonna have to get a line, okay? And what is this line? This line is, let's try to draw this neatly. This line is a y equals m x plus b, right? Sorry about that. Oof. Okay. This line is an mx plus b line, right? So if you remember basic algebra and graphing, this m is the slope, the gradient, and b is our intercept. Now the scientific name of this is m, we call it the beta, right? You see many guys writing it like this, right? Call it beta 1, like this, right? And this guy, the plus b, the y-intercept, is called the bias, right? Bias, right? I'm not gonna do it. Okay, and they write it as beta 0. Okay, so sometimes you'll see them write it like this, but we want to keep it simple. Okay, so we're just gonna write mx plus b. So how do we know how good this line is, right? There's something called a loss function here. Now, before we go into loss functions, we need to look at something called residual, right? Let's get more lines. A line, right? So let's take a data point real quick, right? Let's take, what's a good data point? Here. You think so? Targeting this fella here, right? Can you see? Yeah, that guy, right? So let's see. Let's first draw some lines again, okay? From here up to here, right? And from where else? Here to here, okay? Now, let me get the pen back. So if you look at this point over here, right? We predicted, our regression line predicted that at this point, at 9 years of experience, you're gonna get 10,000, right? You're gonna get 10,000. When in reality, this guy got, we could say 11,000, right? Got much more than your predicted value, right? Now this difference, this line here, we call it residual, right? Residual, okay? Now this is bad. A lot of residual gives us an inaccurate regression line, which is very bad. So we want to find the regression line, the m and the b, that give the line that gives us the least residual per point, right? And that is what the loss function calculates, right? Loss function calculates how bad is your line. What is the rate of error, okay? So one loss function that we're going to use is the mean squared error, right? I should stop going with both fingers. Okay. Oh, do you see that? Okay, the MSE. MSE, right? That's called the mean squared error, right? How does it work? Okay, it's simply, you take this, the predicted point, and you you take the predicted point, and you minus the observed point, and you square it, and you add all of them together, right? So let me just draw the maths of it, right? So simply, you take a summation. Summation is simply a for loop. Go through each one of them and add them together, right? Simple as that. And we can start with I equals 1 at the start, and we go up to n for n data points. Just trying to draw with a mouse. I haven't done that before. Wow, do you see that? N, right? And you can draw some nice brackets. We're also going to square it. And we take the predicted value. You draw it like this, with a caret on top, I, and you minus your observed value, right? The real value. Okay? And we square that. And we divide it by n, okay? Which gives us a nice average, right? So, I know it looks odd, so let's go through this. Y caret, what is y caret, right? Y caret. This is our predicted value, right? So for I, which is the x, we predicted that it's going to be mx plus b, right? So we take m, x, which is I, plus b, the intercept. And we find it different from our observed value, right? Yi equals, let's see, so let's use our real example here. So this is the literal real data. I think there's a text option, but why not? Okay, so let's do this. Put some arrows. I'm gonna do this on paper after and take photos and put it in some place. So don't worry, you don't have to look at this. Okay, so let's see this. Okay, 10k. So that was our predicted. 10k. where the real value was 11k, right? 11k. So that's our error, right? Bam. 10k, so we have negative 1k, right? That's the difference, and we square it. This helps to avoid cancelling off, because assume this is negative. The next item, we undershoot it, hence it's positive. Bam, it's going to cancel out, right? But no, we square it, right? And that's just a smart way of just avoiding cancelling it out, right? And we assume there's what? There are 30 points here, so we're going to divide it by 30 to find mean square, so basically the average, right? And that's what this whole thing is about, the mean squared error, right? Bam. And we want to find the m and the b, which gives us the least amount of mean squared error, right? So we can rewrite this mean squared error as equals 1 over n summation or sigma I equals 1 and up to n. Come on, I hate when it draws up to that. Okay, n. And here, instead, we draw mx x I plus b minus our observed y, right? Bam, you square it. It doesn't matter which order you do, you can do the predicted one minus the observed one, or the observed one minus the predicted one. Doesn't matter at all, because you square it, right? So yes, this is the main form of the mean squared error we're going to use, right? Let me try do this, right? So this is our mean squared error, right? And yes, so that's the mean squared error, right? Now, what does the mean squared error what does the mean squared error look like on a graph? Now, if you look at the mean squared error, it's a function. We call it a bivariate function, right? So MSE, MSE is a bivariate function which takes in the parameters of m, the gradient of our regression line, and b, the y-intercept. Right? So this is what our function is, right? So you know normal functions, fx, right? fx, there's just one variable in it, right? Where this guy has two. So it's tricky, right? Because it's not your classic, it's not this guy, right? Looks like classic this, right? There's something, right? No, it's not this, not here, right? This guy looks like this. So we have three axes here. Basically your average 3D graph. How can I draw this? I had a drawing somewhere. Okay. Actually, you know what? Let's get it. So here it is. Here's what the mean squared error looks like, right? Three axes, the mean squared error, the b-intercept, and the slope. And it's like some kind of bed sheet, you can call it, right? Some quilt, right? Think of it like that, right? A towel, right? I'm not going to draw that, no. So this is what it looks like, right? Now the mean squared error is our error function, right? So we want to find the parameters, these two, which gives us the least amount of mean squared error, right? So going back to this image, let's try to see. So one way I like to think of it is you throw a ball onto here, right? It's going to roll to the bottom, isn't it? Likewise, assume this is the bottom, right? Here. Now, if you look at roughly 2.5 and 1, right? Those two values of m and b give us the least amount of mean squared error, right? So it's quite simple if we had a ball and we had a real bedsheet to visualize it, but computers, no, they do not have that. So how can we find this lowest point in this? The answer is gradient descent. Okay, now the gradient descent. So, what is the gradient descent? So let's first do a really simple example here. So let's go for green. So let's choose a normal quadratic, right? Looks like this, okay? And our aim here is to find the minimum point here. Now, we do not know the equation of this quadratic, hence we cannot use calculus to just find a second derivative and find the minimum point like that, right? So instead we're going to have to use a gradient descent. Now the gradient descent is an iteration formula which converges, right? So if you look at what converging is, right? Go up a bit. So converging, right? So basically, if you remember like what a Lun function looks like, right? I think it's something like this. Right? Basically, if you look at this function, right? At around here, right? It converges to this value. Right? You have a value that it converges to, right? As x tends to infinity, right? That you reach a static that, right? It doesn't change, right? So that's basically what it means to converge. And iteration formula is where you keep changing something over and over. You keep overwriting itself over and over, right? I know that doesn't make sense, but I'll show you in a second, okay? So if you look at the real gradient descent formula, right? So the formula is, so assume we basically have a starting point, right? Could be any starting point, doesn't matter. But our aim is to get to the bottom here, right? So what we do is we do x, we rewrite x equals, so this initial point, right? So x can equal whatever, and our iteration formula is x equals x minus alpha, which is the learning rate, and into the gradient. Write it properly. dy over dx at that point, right? Now let's see what the alpha is, right? This guy. So this is our learning rate, right? So alpha. No, let's go off it. Okay, the alpha. So the alpha, this is our learning rate. Basically, could think of it like the intervals to go, right? How big do you want each step to be? Because our iteration formula is going to be like, it's going to keep going bang, 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 you know, keep going like this. Kind of like a, I don't know if you can see my mouse, but yes, from here. So wait, let me draw it. So from here to here, to here, to here, here, to here, here, to here, to here, to here, till it eventually reaches our center point, right? And the alpha learning rate tells us, okay, how big do you want your step to be, roughly, right? So if we close that, so wait, in essence, it's really going to be like this, right? Keep going like this, this, till you go a bit above, keep, and then you eventually start to converge here, right? So that's what the whole thing will look like, right? Now, if we look at the different alphas, right? We need to make sure our alpha is just right. So if it's too low, we'll end up going very small steps, right? Where's it? Here, right? It will end up going like this, you know, practically like impossible to reach. It will take forever, right? Too inefficient, right? If our alpha is too big, it'll end up going like this, right? Bang, 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 massive steps, right? And it will be impossible to manage, right? And you rarely converge. You won't converge, right? Because your steps are just gigantic, right? So we need to, so usually people say alpha, that they give it 0.0 connected 0.1. That's a sensible alpha, right? At least it works for our linear regression, okay? So we're going to use that, okay? And that's quite a decent one, right? It allows us to go normally in most circumstances, right? So that's what the alpha is, right? And the gradient. Now, let's look at what the gradient has. So that's where the name comes, gradient descent. You're going through the gradient, right? So let's choose blue. And gradient. So if you look at this quadratic, right? The gradient at its stationary point is 0, right? And let's choose a gradient here. 1, gradient here. 2, gradient 3, gradient here, 3, and gradient 4, right? Let's go through what they mean, right? So if you look at point 1, right, the gradient looks like this. It's going down, and it's quite steep, right? Straight line, and it's negative, right? And it's a high gradient, because if you look, right, in a very short span of x, right, we go down massively, right? So that means it's a very high gradient, right? So it's a high gradient. The value of it, the number value is quite high. It's probably like, what, 4 or 5, right? Now if you look at number 2, the gradient is more flat, more like this, right? More resting, right? Still, it's a negative gradient. You're going down here, but in a long value of x, you just go down by just a little, right? Look at the triangle, whereas here, short value of x, go a lot, right? Whereas here, long x, go down just a little. So it's a low gradient. Could be 0 point something, right? Now if you look at 3, right? The gradient, very high gradient, right? But this time it's positive, right? You're going up, right? And it's a high gradient, and as you can guess for 4, it's a very low gradient, but positive still, right? 4 looks like something like that, right? Positive, but low, right? So these are our gradients, right? And where's my mouse? Okay, it's a blue dot, hence I can't see it, right? So now, if you look at this gradient, so this is a gradient, and this is the alpha 0.1 learning rate, right? And again, right, another thing to notice is the sign, right? Let's make this what color now? Purple, right? So if you look at the sign, right? If we look, right, at a negative gradient, right? If we're negative, right? To reach the center, what do we need to do? We need to make it a positive, right? We need to add. We need to go in this direction, right? Go in the positive direction. Whereas if you look at this gradient, it's a positive one, right? You're past to 0. Hence, to go towards 0, you must make it negative and go in that direction, right? Hence, when we multiply with the gradient, this gradient is a negative gradient. Hence, we need to add. We need to add to our original x, right? And to add, we change the sign. Hence, it's a minus, right? So that's what we're doing here, right? So that's what the minus is for. Okay. And how does it converge, right? So let's get yet again another color, pink. I don't think I've used that. Yes, I haven't. So if you look at this, right, how it converges, x equals x minus alpha into the gradient. So if you look at its flow here, so here, as it keeps going, right, the gradient in this area, right, close to 0, almost nothing, meaning that this whole thing, this whole change, ignore the x, that becomes, it tends to 0, right? As you get closer and closer to your point, it becomes smaller and smaller, right? Meaning that it will eventually converge, won't it? As this whole thing becomes 0, bam, you've reached your converging point, which is the lowest point, right? So this is a very simple example of the gradient descent on a quadratic. Okay, now let's implement this gradient descent on our bivariate loss function, the MSE. Let's get some room real quick. Let's see a good macro place to do it. Come on now, easy. How about over here? Yeah. Okay. So now with our MSE, right? Remember it's bivariate. So MSE. It takes in two parameters, M and B, the bias. Okay? So now we want to find the lowest point in this function. So here's what it looks like. And we want to find our lowest point. So, and if you remember the gradient, right? Okay, let's go back. The gradient, right? The gradient descent function. Basically, the learning rate into the gradient at that point, and you keep going from the gradient downwards, right? High gradient, go backwards, and so on, right? So, if we look at this, if we look at the MSE, oh dear, how can I navigate now? Okay, MSE here, right? So, the MSE is, this is the formula for the MSE. Eek. Come on. B and minus our observed value, right? Squared, whole thing squared. So this is our formula, right? The function for the MSE. Now we want to find the lowest point in this via the gradient descent. But we've got two variables at play here, right? Hence, we're going to use something called partial derivatives. So, let's zoom out. Let's go up, actually. And partial derivatives. Oh, we're touching that area. Okay, partial derivatives, right? Partial... I think there's a text function, actually. Let's use that. Partial derivatives. Come on now. Derivatives. Okay? So this is what we're going to use here, right? What is partial derivatives? What does that mean? Partial derivatives is essentially differentiating a bivariate function, or a function with many variables, with respect to one variable, right? So assume, let's use a normal example, right? We have a function f xy, right? xy, right? Let's say it is, what? 2x squared plus 3x y plus y cubed, right? Now, come on now, okay, let's call this m. M is a function of 2, right? So now we want to find the rate of change of m with respect to just one variable. Now, how is that done? It's simple. We just treat the other guy as a constant, okay? So, when it's not implicit differentiation, we're just simply treating the other variable as a constant, okay? So, partial derivative, let me write that. Finding the rate of change of the overall function with respect to just one variable. So this is done. This is done by treating the other variable as a constant, right? Okay, so that's essentially what we're doing here. So let's differentiate m. Okay, so let's do dm. So the derivative of m with respect to x. We're finding how how the change of x changes the overall function, right? So we can do equals, and let's differentiate all the x terms, right? So 2x squared, that becomes 4x. 3y, so that's our coefficient, and our exponent is 1, so it becomes simply 3y plus 3y. And if you look at y cubed, it's an x0 term, hence it's a 0, it's a constant. So this is our partial derivative of m with respect to just x, okay? Now let's do the same for y. Keep it inside too. So if we do dm with respect to y, can equal that to, okay, so if you look here, there's no y term, it's a y0 term, hence that's, we lose that, constant. And 3x, that's our coefficient, multiply by 1, 3x, y0, hence, and y cubed becomes simply 3y squared, yeah? Okay, so ugly y's. You can see it's y. Okay, so that is partial derivatives. Now let's bring it back to here. By the way, summations. How do we differentiate a summation? It's simple, right? Well, if you look at a summation, let's do from 1 to n, right? Let's look at r, but n, okay? And let's just do y I, right? I equals 1. So if we want to differentiate this, right? If you look at what the summation is, if we expand it, it's simply y1 plus y2, and so on, all the way up till yn, right? So that's what the summation is. Hence, if we want to differentiate this, right? Find the whole derivative of this whole thing, right? Simply expand it and do like this, right? But that's the same as this, isn't it? Just simply differentiate the guy inside, right? Inside the summation. You ignore the summation because essentially it's the same thing, right? 1. So it's all the same. So likewise, summation, you don't have to worry about the summation, right? If it's one of those product things, I think the pi, is it like this? I haven't learned this yet, but if it's like this, then yeah, we might have to worry, but it's not. So we can simply just differentiate as usual, okay? Where is it now? Here we are. Okay, so let's find the partial derivatives of this, right? So d MSE with respect to m, right? So partial derivatives. Okay, so some basic calculus. It's a square, so let's use the, what's it? Substitution? No, it's chain rule, sorry. Chain rule, yes, okay. So ignore summation. So if you look at this, differentiate u, right? Bam, 2 comes forward. So wait, ignore the summation. Nah, let's just do it, right? So u to the power of 2, bam, 2 comes, so get a 2 like that. N. And with u, and now we need to multiply by u's derivative. U, so we're differentiating with respect to m, right? So bam, this has no m term, constant gone, b is constant, m, so there's xi, which is coefficient, and m, hence just take out what? Xi, right? So if we look at the summation stays the same, ranges don't change at all, 1, and n, and if we look at this, okay, same u, we didn't touch the inside, xi plus b minus yi squared, right? No, not squared, it's 1 because it's we differentiated the whole thing, right? And we multiplied by the derivative of u, the inside guy, so which is simply xi, right? I like that. So that's our derivative for with respect to m. Now for b, similar thing. D respects to, we'll have space, should, right? With b, right? So if you look at that, similarly, chain rule, so it's going to be 2 over n. And same summation, I equals, start with 1 and n, and inside stay the same, mx, takes me a while, isn't it, plus b minus our observed value yi, and to the power of 1. And this time we have one b term, so yeah, this is it, because constant gone, b becomes 1, right? So yeah, into 1. So those are our partial derivatives, right? And now, so now, where are we? Okay, here. Wait a minute, oh, somewhere, okay, no, here. So here, our gradient, it's going to be the exact same thing, right? So on each iteration, let's draw that here actually. So if you look on, how much space have we got? Okay, so if you look at each iteration, right, let's do a different color so things won't get muddled. So each iteration, so that formula was x equals x minus our learning rate, alpha, 0.1, into the gradient, right? So now, instead, it's going to look like this on each iteration, right? It will be m, we're going to keep iterating over m equals m minus alpha into the partial derivative of m, right? D over dm, right? So essentially what this does is, right, if we go back to our image here, we're doing the same thing. So there are two factors at play here, right? And wait, by the way, and with this gradient here, this partial derivative, we're just keeping b as a constant, right? So we have our initial m and b, our initial guesses, so m equals something, b equals something, and let's put x as well for the example, equals something. So if you look at these examples, right, so m equals the derivative of, the partial derivative of m, right, which will be this whole thing, so current m, and we're going to treat b as a constant, right, and b, right, equals b minus our learning rate into d over db, right? So this block is going to be recurred, right? We're going to keep changing this over and over, right? So in the meanwhile, so let's see what happens in loop 1, right? Loop 1, bam, we have these two default ones, right? Then m equals alpha, so we're going to put m in, and we're going to keep a static b, that we're just going to pull in that b, right? We're not looking at the rate of change, right? So if you look here, the gradient, right? We're just looking at how our m, the gradient in m's direction, basically, right? So it's quite complex, because actually let's try to get that image in. Here we are. Okay. We now stop. Okay, cool. So if you look here, right? Let's make that a bit small, actually. Okay, like this. So if we look at what happens with the gradient, right? There's an m gradient, slope, and b gradient, right? So we can go this way, right? Straight, or we can go this way, right? So this way is the slope way, right? This way, right, is our slope way, and going this way would be our B intercept way, right? So the partial derivatives look at, okay, the gradient in this direction, while treating B as a constant, right? So in this line, right? Look at this line, right? You know, that whole line, where B is just a single 0.5, okay? Where's the lowest to go in this way, right? Similarly in this one, right, you have this line, right? Some kind of curvature like this, right? And at M is constant, what's the best value for B? So that's how they kind of, you know, change over. So first round, okay, where are we lowest here? Okay, here. Okay, this is our new M value. And B is like, okay, from here now, where's our lowest B value? And so on and so forth till it eventually converges to some random place, right? So that is the idea of what's happening, right? Going back here, this is how it's implemented. We treat the other guy as a constant, right? Actually, it would be better to draw some parameters to it too, right? So if you look at here, we pass in M, our M, and static B, right? B, right? And likewise, we pass in a B, a main B, right? Which is changing, and a static M. Well, we're passing M and B, but we're just treating the other two. Other two are just constant, right? We're not looking at those gradients, okay? So that is essentially how the gradient descent works, right? With our bivariate loss function, which is the MSE, okay? And yes, I feel like let's do it in code now. Okay, now let's implement it in code, right? So where were we? We loaded the data and we dumped it in a nice scatter plot. So let's get a generic function on how to draw a regression line, right? So here we are. Here's a simple function. So we're using NumPy. Bad naming, sorry. What's data 0? Y-intercept and slope M. Okay. So B plus MX. It's MX plus B. That's the. Nah, things can keep it out. That's fine. Okay. So this is what the line will look like. What's this? Ah, keyboard is stuck. Okay, let's run all real quick. Load some data. Earth data 1. Come on, didn't edit the line properly, did I? Y equals mx plus b. Bam, here's a nice line. Okay, and again, let's combine it with our scatter plots. Okay, I'm gonna copy more code. So, in essence, let's explain this code real quick. So we're creating a big array from the minimum years of experience to the maximum years of experience, right? And create 100 evenly spaced outputs between them, right? That's a big array of that, and we create a big array of all the y values, and x line, y pred, bam, here's our two big array plotted, right? So that's how we can plot a line. So by combining them with the scatter plot, we're doing the same thing, creating another line, and plotting the scatter plot and plotting the line in the same plot. And you can do that actually, right? And it will look like this, okay? So our aim is, we know what the aim is, okay? So it's defined theta 1 and mx, b, a plus b, and a m, which gives us the best line. So these are the two ones we're going to target, but I'm going to use the name m and b, okay? Let's Control C, right? Okay, like that. And where's the line? This line, right? There we go, okay? And let's make this a function so we can plot it easier, right? So if we copy this, and we don't have to keep importing NumPy either, okay? That's nice. And let's add some code. So def plot, take in parameters of m and b, parameters, and just tab everything, right? Tab like that. Good. That's our beautiful function. And yes, visualize data. Okay, nice. And we can plot it if we wanted to, right? So plot. Let's plot line 1 and 1, right? And since we're using the database, the same data set throughout the whole thing, we don't need to make the dataset dynamic either, right? If we were to, just more parameters, so on, okay? Nice. Here's our line. Okay. So, what do we need first? We need to implement our median squared error, right? Let's not do that. Okay. Space. Right. How can we implement this in Python, right? So, let's create, okay, some text. MSE, right? It's called MSE, right? Why isn't this aligning properly? I just wonder. Okay. Yeah, looks better. Okay. Def MSE. What do we take? We take in an M and a B. As I said before, the what? We need to make this. You can't hard code it, can we? Good spot. We need to make it a dynamic line, okay? So, MSE, what is this? So, basically, we're going to be looping through the whole dataset, right? So, let's get a Y stream, X stream, and a Y stream real quick, right? So, years of, so let's call it Y, years of experience, equals, and data frame, and this is years of experience, right? I'm just gonna add some labels, and X, wait, that was X, wasn't it? X was that, and Y was salary, right? Y salary, 1L, okay, salary, right? Equals data frame, and we take in our salary, right? So those are 2 ones. And the mean squared error, what does it do? It leaps through each of these points, finds our observed value, the real one, and the predicted one, right? So let's do Y. First we gotta loop through all of them, right? So let's start with a for loop. For what do you call this? I. Wait, what is it? What the thing? So they call it I, right? Okay, that's for I in range length of. So it doesn't matter either, both are the same, right? Is that salary? I don't think so. Yeah, it's a little odd, right? Y underscore salary, right? Like that. So for in range, we want the index because we just don't want to loop, right? Hence, or we can do enumerated and just get it done, but it doesn't matter either way, right? So for loop for in range, so this will give us all of the. So if we just print Y underscore salary of I. Okay, we need to call our function too, right? MSE, let's go 1, 1. There we go, all of our salaries, right? So if you look at salaries, 33k, 46k, 33k, 46k, there we go, right? Lowercase I, that's the golden rule, isn't it? Not capita, no one uses capita. So, and there we go. So we're able to loop through each point now, right? Now, the Y. So, observed value equals, this is what the salary, no? Okay, Y salary then, right? So these are our observed values, right? Yes, and we take the X and do a function on it, right? So observed salary is Y, I, right? These are observed ones, right? Now if we look at the predicted ones, that's our line. So equals Y equals MX, X years of experience, plus C. So Y equals M into X years of experience, I. Let's add some brackets so that bottomless is a sure shot, plus B, right? Predicted, right? So that's what this is. And so mean squared. No, so this is what the error is, right? That's why it's called mean squared error, right? Because you're finding the mean, right? You're dividing by n. That's why it's called it. Okay, got it now. Right. Okay. Anyway, so it's the predicted minus observed, right? So predicted minus observed, right? Observed value, and we exponentiate it to 2, square it, power of 2. So that's our error, right? Take this and you add it. So let's have an outside, let's call it sum, right? Summation. There's a function, summation of errors, right? There's a function called sum, right? So we don't want to touch it. And summation of errors equals summation, I think you can do plus equals, but why not, huh? Error, right? Adding the square. So square it, then add it to the main count, right? And at the end, we're going to return, let's not print, return summation of errors divided by length of y salary, right? Basically n, or it doesn't matter either. And no, it cannot be in the for loop, sorry. Like that. Good. So there's our MSE, right? So with 1, 1, we're gonna have a horrible MSE. Print lowercase. We didn't rerun that. What's the problem with stupid numbers? So we have, wow, look at that mean squared error, huh? It's in the, what, millions, billions, no? That's in the billions. Okay, so that's our mean squared error with this. So you take residual, I explained it here, right? So all this residual, right? Add it up, you get billion, right? Okay, so there's our mean squared error function ready, right? So this is the file that we're gonna try find the minimum of. Okay. Okay, now let's create some functions for the partial derivatives, okay? So text partial derivatives, right? Let's create a function, nice little function for that, right? Okay, some code. Let's call it partial derivative of who? Let's start with m, okay? M and b, we have to still take m and b. So where's our partial derivatives? I keep doing command and mouse, but it's space. Okay, are these our partial derivatives? Yes, they are. Okay, same thing, let's implement it, shall we? So in fact, I'm gonna copy this because we can get a lot from this. Xtrain, no, not train, I'm using train. I did read that recently, and it's okay. Y, summation of errors, okay, good. Looping through it, instead of squaring it, we're not squaring it. And it's 2 into that. And 2 into that, okay. And yeah, oh wait, no. Here, right, 2 into that and into xi, right? So we need to multiply it again by xi. How do we do that now? Into the predicted minus the verb into xi, this guy, right? So that should be our, not kind of turn 2 like that, no. Okay. So that should be our thing ready, right? Double check. Yeah, it looks good. M and B. Treating B as a constant. Okay. Yes. So that's partial derivative of M and partial derivative of B. Copy that. Partial derivative of B. M and B, take it, so all the partial derivative of B, same thing except this is 1, and yeah, okay, so we do not multiply it, it's 1, and same 2, partial derivative of B, nice, so looks good, yeah, Okay, so there are our partial derivatives now, okay? Okay, now for the fun bit, the gradient descent, the actual bit. So, the gradient descent, Yes, okay. So let's go back to our planning and let's start implementing this, okay? So, first let's initialize the variables, okay? Starting with the alpha, okay? So, alpha, we're gonna set it to the 0.01 standard one, okay? And we have an m and b. So let's set some initial values, okay? For start, we'll use 1 and 1, okay? A flat line. M and b, right? It's gonna have a big mean square error, but it will converge after some iterations, okay? Next up, let's see how much iterations to do, right? So max iterations equals 1000. So later on we can edit this loop to actually stop when it converges, right? But for now we'll just do it 1000 times bluntly, okay? For simplicity. So the loop for I in range, and let's just do max iterations. Okay, so we're not going to use I, so doesn't matter. Anyways, okay, so if we look at this chart here, right, we're just going to keep on updating m within the loop. So let's do that. So m equals m minus alpha into the gradient at that point, okay? So we're going to take the partial derivative of m here, and we'll pass in m and b. B is constant and m is the one that will change itself. And for b, same thing, b minus alpha into the partial derivative of b, and then we pass m and b into it, right? As so. Okay, and this should be it, and we should get a regression line. So first let's plot before m and b, and let's plot after as well. Okay, and let's run all, and we should see the two lines. Here we go. So here's our first line. Here we are. So with m and b as 1, here we go. Not at all. And after the 10,000 iteration, we've got our good m and b, and as you can see, it looks quite good, quite standard. Yes. So let's print out some data, right? So we can print. Let's get a string. So after, let's do max iterations. After how many max iterations? Okay, nope. Just copy that. After max iterations, to 10,000 iterations, m is, let's put m, and b is b, as so, okay? So if we print that data, so m is roughly 9,000 something, and b is 24,000, so looks quite good, yes. And we can also print the mean squared error for this too, right, with this pair. So MSE is, we can take the, is that the function we give? Yep, MSE, and we can pass m and b. Okay. And this pair gives us an MSE of about, wow, 30 some big number, but because our data set, right, 60,000, 80,000, 120,000, it's quite big numbers, hence the MSE it could be quite big, right? Even though it's not really such inaccuracy, it's just was at such a big scale, right? Hence it's that big. So yes, that's our gradient descent. And finally, let's visualize the MSE too. Okay, so we can actually save all the values of our MSE. So let's create a MSE history array, and let's put in MSE M and B, right? A first value, right? And continuously we can append, so MSE history dot append, and we can put in the MSEs, right? And afterwards we can plot that over into a matplotlib chart. Okay, so if we add some more code, so let's visualize data visual, or let's call it metrics. Okay, metrics, put it up and here. So let's rerun this. There we go, and now it should run. Let me see, is that the name we gave? Nope. Here we go. So this is what the MSE looks like. So it converges quite quickly. So it seems like we do not really need a 10,000 round. So roughly by 400, it already converges. And additionally, we can draw ourselves a nice heat map. So this is not my code, but I'm just gonna leave it here. This is quite cool. Yes. So this is a heat map of the MSE. So the darkest spot, which is about here, that's our optimal place, right? Lowest point. So if we look at our MSE, how it looks, right? 24, is that, yes, that's 24K. 24K, roughly around here, yes. Here, and if you look at, what now? 31 million. So you can see it's quite different, quite somewhere along this line. So one pitfall from the gradient descent is that if, assume our landscape, right, this big function here, right, if there are two minimums, right, our gradient descent could get trapped into one of those, which would cause a false minimum to be reached, right? So that could be the situation happening here. Like if we extend this big time, right, there might be somewhere around here, right, another minimum which the MSE has fallen into, which seems like the case because we're right now at the 10,000s here, right, where they're talking the millions on this side, somewhere far beyond that side it has fallen in. Okay, so that's one downside. A quick fix for that is you could start from many different places, right? So it wouldn't exactly fall. So if you look here, right, if we start from here, we'll trickle down. If we start from here, if there's another minimum somewhere else, it could trickle down into there. So likewise, you could start from many different places, and you could probably avoid that pitfall. So yeah, that's a full course video on the linear regression, which we were able to get. And one way you could make this better is that you could use different loss functions, right? But the median squared error, it might not be the best loss function out there, right? And in terms of both accuracy and efficiency, like how much memory usage, all that stuff, speed, but this is just a 30-piece data set, hence not too bad. If you make it like massive, right, it could get quite chunky. Additionally, what probably could cover next is a polynomial regression line. Instead of having it to 1 degree, y equals mx plus c, you can have it to x squared if there's those, overall trends, or cubic if there's quite, such data, right? And then you simply have much more partial derivatives with respect to that, and it will take a lot more processing as well. Additionally, you can have different dimensions, so not just salary and years of experience, you can have multiple columns, right? So that too you could add. So that would have much more dimensions and much more betas, they call it, right? So here if you look at the equation line, right? The equation line, instead of y equals beta, let's draw beta for now, beta 1 x 1 plus beta 0, instead of this, for multi-dimension data, right, it will be like this. So y equals beta 1 x1 plus beta 2, and so on for each column, right? Beta 2 x0 and so on till you get till you reach the end. So that's what a multi-column data set would look like. So yes, this is the gradient descent, and hope it helped.